let's pick a example for plane stress problem. Let's say that I have a bracket. So I'm going to try and draw a bracket for you, try and best represent it as to what it should actually look like. It sort of looks decent enough. So if this is a bracket which is used to load structures or put it on the wall for some kind of load bearing capacity, then if I draw just the side view of it, then it looks like this. In general, we know that the back edge which you don't see is the one that is going to be fixed to the wall. Okay, so that is the wall, that is the edge that is going to be fixed to the wall completely. So this is constrained, and then there's going to be a load which acts on the top surface over here, and this is a, let's say this is a varying load according to the length in this direction. So you have two different conditions to it. If I draw it on the two-dimensional side, then I know that this is now clamped, and there is a varying load which is higher at this edge and lower at this edge, somewhat like this. And of course it is the same through the thickness of the bracket. So either I could start by making this into a two-dimensional problem. So I could say, okay, this would become plate number 1, this would become plate number 2. So basically I would have one plate here thin, another one like this, and then I would have to make sure that I have the correct offsets, etc. planned for both the planes, and then apply the different loads and make sure they are joint at this edge in the assembly, or in Patra-Nastran I would make sure the nodes are equivalent so that they are fused at that location, and then run the analysis for different load conditions and different boundary conditions. Now if you actually look at it more critically, you can say that if I take any slice of the structure, the change in the thickness direction of the deformation of the behavior of the member is not going to change. That means I have the load which is acting on the top surface of this bracket, and it's the same across every section of the bracket if I make slices of it. Therefore and the boundary condition is also the same. Now if I make a new midplane of this member, I see that the load is also symmetric about the midplane and the boundary condition is symmetric about the midplane. Therefore, I can easily take a slice of it as a 2D planar structure to make it into a plane stress problem, because all the conditions check. So basically in the thickness direction, which I can take here as Z, I can assume that there is no change in the stresses. So that means sigma ZZ, tau XY, tau XZ, and tau ZYZ are equal to 0. So I can apply plane stress conditions. So what have I done is I have reduced my computational power or computational need from so many elements to just a single surface with minimum number of elements that I could deal with for a plane stress condition. And of course I have a smaller matrix, so I can solve it much faster also for the derived results. So this becomes a plane stress problem. How do we actually apply a plane stress problem in a program? So for example, if we are using Abaqus, then you need to create a 2D planar part as usual. But when you create a section, then you have to create a solid homogeneous section. And when you create a solid homogeneous section and you apply it to your part, then it can ask you to choose between plane to be a standard homogeneous one or a plane stress, plane strain condition. And that's the one, there's a box there, checkbox, you tick it, and then it asks you to give you a thickness of that part. And you know the thickness in this direction, so you can enter the number over here. Now, this is both plane stress and plane strain. To distinguish between which particular case you want to use, when you do the meshing, before meshing, you go to that section which says S4R, you click on that and you assign element, and this element type will be called plane stress element. And that's how you make sure this is a plane stress.